Our mission today is pretty crucial, actually. We're diving deep into environmental statistics. We want to figure out how researchers untangle cause and effect in climate and ecology when things happen over really long timescales.
And the timescale is fundamentally the challenge here. When you're looking at climate change or pollution impacts, maybe fisheries dynamics, these things unfold over years. If we miss a genuine delayed effect, maybe something takes 20 years, like a climate action finally impacting an ecosystem well, we risk basing huge policy decisions on, frankly, bad information.
That's the core issue, yeah. The specific method we're digging into today is quite specialized. It's called testing of long-term Granger causality in environmental time series.
Right. And your traditional statistical tools, the ones that work great for, say, short-term economic forecasting, they often fall short here. If you use standard ways to pick the best model, things like AIC or BIC, they tend to strongly penalize you for including those really large lags, effects that might only appear 10 or even 20 years down the line.
So they almost punish you just for trying to look that far back, because adding those long lags means adding more complexity, more parameters to the model.
Precisely. And besides that penalty, the older methods can be too easily swayed by day-to-day wiggles, the short-term noise. And that noise can essentially drown out the underlying real long-term causal link you're actually hunting for.
Okay. So our goal for you, the listener, is to untack this novel framework. It's designed specifically to slice through that immediate noise and really nail down those critical decades-long causal connections. These connections are absolutely vital for making good predictions and ultimately better policy choices. Right. Let's start with the basics then. What exactly is Granger causality, or GC, in this kind of context?
Simply put, Granger causality is a statistical concept about predictability. That's a pretty straightforward question. If I know the past history of one thing, let's call it time series X, does that knowledge significantly improve my ability to predict the future of another thing, time series Y? If the answer is yes, then we say X is a Granger cause of Y. It's directional.
And it's super useful because, well, in environmental science, you can't run controlled experiments most of the time. You can't just, switch off the Gulf Stream to see what it does to fish numbers. You're stuck with observational data.
Exactly. But, like any tool, GC needs certain conditions to be reliable. First, their stationarity, basically. The statistical heartbeat of the data shouldn't change over time, or you need to adjust the data to make it stationary. Second, the standard framework usually assumes a linear relationship between X and Y. And third, and this is the big one, you have to be pretty confident there aren't some hidden factors, confounding variables driving both X and Y. That could make you think there's a direct link when it's actually spurious.
That linearity assumption feels like a potential sticking point right away. Nature isn't always neat and linear. So what are the specific hurdles that environmental data throws up? Why is it so challenging?
Oh, it's notoriously messy. For one thing, many environmental processes are what we call cyclostationary. Think seasonal cycles, temperature, rainfall patterns. Their statistical properties change predictably over a fixed period, like a year. Standard linear models can really struggle to capture that kind of periodic behavior properly.
And then there are the extremes, right? The 100-year floods, the record heat waves. Those aren't gentle slopes on a graph.
That's the heavy tail distribution issue. Environmental data often shows heavy tails, meaning extreme events happen way more often than you expect from a nice standard bell curve model. Your typical GC tests might just not be robust enough that we get thrown off by those really big infrequent spikes or dips.
Okay, so if the problem is that our standard statistical models get fooled by short-term noise and shy away from long-term effects, what's the solution these researchers came up with? It sounds like it needs to be quite different.
It is, and it feels a bit counterintuitive at first glance. They introduce what's called a restricted autoregressive model. The key move is imposing an intentional lag restriction. Let's call it R. And R has to be greater than 0.
Wait, hang on. So they fixed the problem by deliberately ignoring the most recent data, like telling the model, don't even look at what happened in the last year or two. That sounds backwards.
It does sound backwards, but it's actually quite clever when you think about the goal. If you let the model consider those very recent short lags, standard selection methods will almost always latch onto the immediate noisy relationships. By forcing the model to ignore that immediate past, by setting that exclusion window R to, say, 2 years or 5 years or even 10 years, you basically compel the system to search only for those larger scale long-term connections. You're filtering out the short-term static.
Ah, okay, I see the logic now. You're intentionally blinding the model to the daily or monthly fluctuations, so it's forced to focus on the decade-long patterns underneath. So once you've built this intentionally handicapped model, how do you actually prove it's better? How do you know it found something real?
You use what's called an out-of-sample testing framework. It's all about predictive power. You basically compare the prediction errors you get from your full restricted model against the errors from a simpler nested model, one that doesn't include the past history of X, the variable you're testing for causality.
Right. So the starting assumption, the null hypothesis, is that adding X doesn't help the errors are the same size, whether you include X or not.
Exactly. And what you hope to find, the alternative hypothesis, is that the errors from the full model, the one including X's history beyond lag R, are significantly smaller. That improvement in prediction, that statistical edge, is your evidence that X really is a Granger cause of Y over that specified long term.
And given how messy environmental data is, with those heavy tails and cycles we talked about, they don't just rely on standard formulas for this comparison, right?
No, they use a robust bootstrap algorithm. They actually calculate 4 different measures of prediction error, different ways to quantify how wrong the forecasts are. And the bootstrap method figures out the likely distribution of these error measures empirically, directly from the data itself. This makes the whole comparison much more reliable, even if the data isn't perfectly behaved, not normally distributed.
So the bootstrap is key for making sure the findings hold up in the real world with all its noise and extremes.
Absolutely vital. It provides that robustness that standard tests often lack with this kind of data.
Okay, the theory sounds solid, kind of elegant in its own way, but did it work when they tested it? The simulation study is usually where the rubber meets the road. What happened when they created artificial data where they knew there was only a long-term causal effect buried in there?
This was a really crucial test. They set up a system where X only influenced Y after a significant delay, say 15 or 20 steps later, with noise added in. And when they applied their method, specifically using that restriction setting the exclusion window R to something like 10, they saw a major improvement in test power compared to traditional methods. They got much, much better at actually detecting the true, hidden, long-term causal link they built into the simulation. This is especially true for shorter time series, like 100 data points.
Okay, so that really confirms the core idea. If you genuinely only care about that long-run relationship, deliberately ignoring the short-term noise is the way to find it.
It really drove that point home. And another critical finding was about robustness. They ran simulations using standard, well-behaved normal distributions, and then they ran them again using data with those heavy tails. A t-distribution, specifically which mimics the potential for extreme events. And the results, they found only really trivial differences between the two scenarios. The tests performed almost identically.
That's huge.
Yeah.
It means the method should be reliable even when you're dealing with real-world environmental data, which, as we said, is full of those unexpected spikes and dips, floods, droughts, whatever.
Exactly. It suggests the approach is highly dependable for the kind of messy data environmental scientists actually encounter. Now, they did acknowledge a trade-off, to be fair. In a scenario where both short-term and long-term effects are present, which they call DGP3 in the paper, imposing that restriction word means you will lose some overall predictive power because you're intentionally throwing away the information from those short lags, which does have some predictive value in that specific case. But, for researchers focused squarely on the long-term dynamics for policy reasons, that might be a trade-off they're perfectly willing to make.
All right, let's move from simulations to the real world. How does this statistical approach help uncover insights from actual environmental data? First up, golden tilefish. They looked at the connection between climate indices and commercial landings of golden tilefish, specifically the northern stock off the U.S. coast, using data from way back, 1915 to 2000.
Yeah, a nice long data set. They looked at 3 specific climate indicators. The Annual Atlantic Multidecadal Variability Index, or AMV, version of the AMV focused just on the winter months, December to April, and also the North Atlantic Oscillation, the NAO, again focusing on winter, December through February. And they made a small but important note. Sometimes biologists call the AMV the Atlantic Multidecadal Oscillation, but statistically it's not technically oscillatory. Just a point of clarity.
Good detail. Okay, so they applied their method using an exclusion window of 2 years. What did they find? Did climate drive the fish landings long term?
Well, the broad annual AMV index, generally no. It wasn't consistently identified as a long-term Granger cause. Only one of the 4 test statistics they used showed a significant result, and only just barely.
But I suspect there's a twist coming.
There is. Here's the interesting part for you. Both of the indices focused specifically on the winter months, that winter AMV and the winter NAO, were strongly identified as Granger causes of the tilefish landings. All four of their out-of-sample tests picked up the signal clearly for both winter indices.
Wow. Okay, so it's not just general climate warming or variability over the whole year that matters for these fish populations decades later. It's something specific happening during those critical winter months.
That really highlights the value of the method, doesn't it? The restricted model cut through the annual noise and pinpointed that specific, seasonal, long-term driver.
Precisely. It suggests a much more targeted mechanism linking winter climate conditions to the success of the tilefish fishery years later.
Okay, the second case study zoomed out even further, looking at really long-term climate dynamics. This one investigated the causal links between the North Atlantic Oscillation, the NAO, and sea surface temperatures, SST. And they used a very long data set for this, 160 years from 1855 right up to 2014. Yeah, this gets into some fundamental questions about how the Atlantic climate system works over decades, even centuries. There are competing ideas here.
What are those main competing hypotheses?
Well, idea one is relatively simple. Maybe the ocean just sort of passively reacts to the atmosphere. It integrates the atmospheric noise coming from the NAO over time. Idea two is more complex. It suggests there's a genuine coupled ocean-atmosphere process at play, driving these multi-year climate swings through changes in how heat is transported, potentially involving the big ocean circulation system, the AMOC, the Atlantic Meridional Overturning Circulation. This second idea implies a real structured delayed feedback loop.
So, did their analysis shed light on which idea might be more accurate? What did the raw correlation show first?
When they looked at correlations between filtered versions of the NAO and SST data from 9 different locations, they found a complex pattern. At zero lag, looking at simultaneous relationships, they saw a familiar trapole pattern. Negative correlations at high and low latitudes, positive in the middle. But the really interesting part came when they looked at long lags. They found evidence of a decadal scale signal. Specifically, SSTs tended to be warmer 20 to 30 years after a period of positive NAO. 20 to 30 years, that's a huge delay. It's a massive lag. Think about something happening in the atmosphere today influencing ocean temperatures significantly around, say, 2050. That kind of multi-decade delay really lends support to the second hypothesis, the one involving deep ocean processes like the AMOC.
Okay, so the correlation hints at a long delay. How did the formal long-term Granger Causality test perform here? They used a big exclusion window, right? $10 years.
Yes, they set R10 to really force the focus onto those decadal and multi-decadal links. And it was also pretty compelling. They found that the NAO was a significant long-term Granger cause of SST at 2 specific locations they tested individually. But the evidence was even stronger when they looked at an aggregated time series, basically averaging the SST data across the upper latitudes. For that aggregated series, all 4 of their tests indicated that the NAO Granger caused SST over the long term.
That's interesting. Averaging the data seemed to strengthen the signal. Maybe it reduced some of the local noise.
That seems likely, yes. Aggregation often helps smooth out local variations and reveal the broader underlying pattern. It led to lower p-values, meaning stronger statistical evidence for the causal link. And crucially, when they tested the causality in the other direction, asking if SST leads the NAO over these long timescales, they found much less evidence. Only one statistic suggested a possible link, and only for the aggregated upper latitude series.
So it seems to point towards a clearer directional influence. The atmosphere, NAO, influencing the ocean, SST, decades later rather than the other way around, supporting that complex coupled system idea.
That's certainly what the results suggest, yeah. A long-term lagged response of the ocean to atmospheric forcing.
So let's wrap this up. What's the big takeaway here for you, the listener? I think the key point is that this novel statistical method seems like a real game changer for environmental science. By cleverly using these lag restrictions to ignore the short-term chatter, researchers can now more robustly find and confirm these really important long-term causal links.
Exactly. Whether it's understanding how winter climate drives fish stocks years later, or how the atmosphere and ocean interact over multiple decades, it gives scientists and hopefully policymakers more confidence in identifying these slow-moving but critical cause and effect relationships. It helps filter out the noise and focus on the signals that matter for long-range planning and understanding deep environmental processes.
It definitely provides a powerful tool, but it also raises a fascinating question, doesn't it? Something to think about moving forward. The current method, as powerful as it is, relies on picking a fixed lag structure. Beforehand, you choose your exclusion window, you choose your maximum lag K.
Right. But we know intuitively and from other research that real-world environmental systems are often more complex than that. Causal relationships might not have fixed delays. Think about it. Could the lag time between, say, a climate shift and an ecological response actually change over time, maybe as the overall system becomes more or less stable? Or perhaps different events trigger responses with different delays? So moving beyond these static lag assumptions, exploring methods that allow for variable lags or time-varying causality, that seems like the next really exciting and probably quite challenging frontier for researchers in this field. How do we model causal links when the delay itself might be changing?
A really provocative thought to end on. How do we track causes when the echoes change their timing? That's definitely something.